Welcome to the 19th lecture video for Physics 4C. We covered the key semi-classical models in the previous lecture, and we are preparing for the introduction to the fully quantum mechanical approach that we will start next week. So, in this lecture, we will cover a couple interesting topics that didn't quite fit into either, while nonetheless being useful for when we go deeper into wave mechanics and atomic physics later. First is the full presentation of the Stern-Gerlach experiment, briefly mentioned in the previous lecture as giving experimental support to the Bohr's nonsensical assumption of angular momentum quantization. There is something of a historical inaccuracy in how this experiment is treated in the textbook, so I will highlight that with the related accidents of physical parameters. The second is the Fourier analysis, or decomposition of periodic functions into Fourier components, that is, an infinite series of sine and cosine functions. A good understanding of Fourier decomposition can help facilitate development of good quantum mechanical intuition as we get into wave mechanical formulation of quantum mechanics. This is it for this week. Next week, we introduce the new methods and tools we will need for the fully quantum mechanical treatment of physical systems.
So this is the Stern-Gerlach experiment setup. What they've done is they had an atomic beam apparatus that allows people to do things to the beam of atoms and and that help to figure out the properties of the beam. I think you might have seen in physics 4B about things like a charge to mass ratio. The way you do experiments like that determining charge to mass ratio is you get beam of the charged particle and you put them in a magnetic field, you see what kind of circles they make, and that allows you to calculate charge to mass ratio. In this experiment, they are actually using neutral atoms, silver atoms. And the main reason they were using silver atoms is, so theoretically it would have been the simplest if they used hydrogen atom, but hydrogen atom doesn't have the right chemical property to be used the same way beam of silver atoms can be used. So they use silver atom, but the goal here is that because the silver atom has one unpaired valence electron, in certain ways, the kind of property they were looking for would be quite similar to hydrogen atom. So they could do experiment with the silver atom and infer the infer properties of hydrogen atom based on what they observed with this. And I guess simple description here is this is what they saw, and so they had a beam of neutral silver atom. So because they're neutral, if you put it in an electric field, it wouldn't do anything. In a magnetic field, they had a reason to suspect it might do something. So this is a non-uniform magnetic field, and it's designed to exert a force on a magnetic dipole that I'll talk about in a little bit. Um, and they were looking for, okay, what kind of splitting will this magnetic field cause on the silver atom? And again, your textbook ties this to electron spin, which is correct enough physically, but not historically. So let me step back a little bit and approach this again from a more historically correct perspective. And for that, what I would like to do actually is to go to this article from Physics Today, which is published by American Physical Society, that gives a good overview of Stern-Gerlach experiment. It's titled "How a Bad Cigar Helped to Reorient Atomic Physics." I recommend that you read through it. It's. I remember reading it as a student, and it was fun reading through. And it's a colorful tale of how um, so I'm kind of come from a biased place in that my own training is in experimental physics, not theoretical physics. And it is my opinion that experimental physics is harder than theoretical physics. And, which may not be universally shared. Sometimes theorists think they are the smart ones. um, and some part of this story will tell you why experimental physics is often harder than theoretical physics. So I'm not gonna actually read it through the whole thing in this session. I'll leave that for you. I'll stop at the appropriate places to highlight what Stern and Gerlach were looking for, what they found in their experiment, and how they interpreted it at the time. So, um, so I guess, hmm, where should I start? So, oh, I think this clock actually has, yeah, the experimental setup for the apparatus. So maybe that's a good place to start. So what this is illustrating is the figure that you saw in the textbook section. It's showing the physical Stern-Gerlach apparatus. You have a beam of neutral atom. They are made to go through a non-uniform magnetic field, and there's a result that they found. And maybe the first thing to do is step back and ask the question, what were they hoping to find? And what they were hoping to find is they were hoping to test what I think is quoted in the article as them saying this nonsense of force. So this is the nonsense of force as they understood it. So Bohr's nonsensical semi-classical model says that. So this is, I guess, so this is what you will read in section 6.4, the Bohr model. So in Bohr model, what Niels Bohr hypothesized was that when you have a model of an atom with a nucleus, so in case of hydrogen atom, it would be proton that is 1800 times as massive as electron. So quite nearly all of the mass of the atom is at the center. And he was suggesting that the way the electron is stably arranged with this atomic nucleus, so here's my electron, is that it's set in a stable orbit. And the way it is stable, unlike the classical prediction, which would have predicted that this is going to spiral into the nucleus as the electron emits electromagnetic radiation. That's the classical prediction. And Bohr's nonsense was to impose this condition without quite as much justification as there should be, that as this electron orbits the nucleus, that it has quantized angular momentum. Its orbital angular momentum comes only in discrete units of h bar. And as a reminder, h bar simply means h over 2 pi. And he's setting this so that this n has to be integer. In fact, in this model, n would have to be a positive integer, because in Bohr's model, if n is equal to 0, then electron isn't really orbiting, and all of this wouldn't work out. So n goes from 1 to and so on. So what we associate with the ground state, the lowest energy state of a hydrogen atom, would be associated with the n equals 1 state, where the electron has orbital angular momentum over h bar. All right, so it's sometimes it's hard to find difference between the classical myth telling and physical models, because we like to look at the Greek mythology as an example of myth, as one of the first attempts at explaining our world. Where did the world come from? It came from, I don't know, decapitated the head of a titan or whatever. And which is not what we believe. Um, and the difference between the ancient myths and the modern models is that we follow the consequences of modern models. if we truly believe that an atom is made of one charged particle, a positive charge, that is being orbited by a negative charge, there are going to be consequences. There's going to be additional predictions that wasn't originally part of what was model was trying to take into account. Originally, all that the model was trying to explain was the Rydberg formula. That somehow the Rydberg formula made sense if you made atomic energy levels go as minus 1 over n squared. And Bohr's model, quote unquote, drives that back. And so that would be kind of the starting place for the model. But it doesn't, but there are other consequences that you can deduce from taking this model seriously and looking at this as, okay, I have a charged particle that's going in circles. Then what this begins to look like is a current loop. So, so what this becomes is you have something that is some sensual fashion is a loop of current. And I guess if so I'm gonna say my electron was actually going clockwise, that would make my current go counterclockwise. And if you think back to what you learned in physics 4b, when you have a current loop like this, then there are consequences that follow from that. One is, I guess, oh, this should actually generate a magnetic field. So from the view that I've drawn, you would have magnetic fields that, let's see, I'm trying to use my right hand rule. So, as your current goes counterclockwise, you would have magnetic field that's coming out of the screen. So I have magnetic fields that's coming out here. And on the outside of the loop, I have magnetic field that's going into the screen. And if I draw the different view or side view, then it looks like this. You have, so this is the positive stationary charge, and my negative, my current is kind of going in a circle that looks from side view this way. And I'm gonna say my current goes into the screen here and comes out of the screen here. And the magnetic field due to a loop of current that looks like that, looks like this. So as you imagine these consequences of a Bohr's model of an electron going in circle somehow stably around the atomic nucleus, you come to the realization that what Bohr model predicts is that an atom should behave like a magnetic dipole. This is the elementary model of magnetic dipole. So that's the starting place or motivation for the Stern-Gerlach apparatus. Because, okay, we have a model of atoms that says atoms should behave like magnetic dipole. So we can do magnetic things to it, see how they behave under the imposed magnetic field, and see if what we get experimentally matches the prediction of Bohr, which is that this orbital angular momentum is quantized. So the magnetic dipole, which is associated with the amount of current, the magnetic dipole moment in terms of current, if you remember the formulas in physics 4a, the magnetic dipole moment is given by current times the area. And if you have the speed of the electron, you can kind of get an equivalent value for current, number of, in some sense, dqdt, and the area of the circle, and you can come up with a value for magnetic dipole. And this would be an experimental prediction that you can test. If Bohr is truly right about the orbital angular momentum being quantized, that would lead to the quantization of the amount of current that can, it would lead to the quantization of this quantity, current times the area, because there are very specific allowed orbits that fixes the amount, the area that can be enclosed in the current loop. and there's some specific amount of current that's associated with that area. So that would lead to a quantized magnetic dipole moment. So it's a prediction. It's not something that anyone had measured before came up with this model. So this is a genuine prediction. It's not an attempt at explaining the world as we see it. So and this again, this is what sets apart the classical mythology from the modern scientific process. When we come up with a model, whether it be the decapitated head of Titan or a model of an atom like this, we follow its consequences. And with the decapitated head of Titan, we don't follow the consequences. There's no way to. But with this model, you can. And Stern and Gerlach did. And this apparatus, it uses this inhomogeneous magnetic field to apply force on the dipole. The way the magnetic field is set up, if the magnetic dipole is aligned one way, it would feel a force one way. And if a magnetic dipole is aligned the other way, it would feel the force the other way. So what you might expect is um, so if this was some classical arrangement with the angular momentum that could take any continuous set of values, then you might expect some kind of spreading of the atomic beam, but you wouldn't expect this bimodal distribution with one distinct value and a second distinct value. You would kind of expect it to be just generally spread out. And when Stern and Gerlach did their experiment, what they found is that, and there's a nice bit of a historical uh, trivia, not trivia, is that when they did the experiment and after smoking the cigar that the story refers to, they discovered the well-separated bands of silver deposits. They sent this congratulatory postcard to Bohr. So this is the postcard that's in the story, and I think it's written in German. It's beer. I think that's a we for German. I can't read it all, but what I will point out is this is their picture of the silver deposit without magnetic field. So that's just showing the atomic beam, and when they apply magnetic field, they see clear separation of the silver deposit, which they took to be evidence of quantization of angular momentum. So nice story. I think if you think about it a little bit, or read through the actual story, then I hope you will notice a bit of discrepancy between how your textbook treats Stern-Gerlach experiment and and how this description and comparison of Bohr's model, how they don't quite match up. Because in your textbook, they treat the Stern-Gerlach experiment as providing the evidence for electron spin, and physically that is correct. But at the time of the Bohr's model and at the time of a Stern-Gerlach experiment, we didn't really know about the quantum mechanical spin, which we'll talk about, I think, in about 2 weeks. So here we are talking about angular momentum, and spin is also a kind of angular momentum, but we are strictly talking of orbital angular momentum. And it's to me, it's beautiful how certain coincidences work out in a way that some of the misunderstandings in Bohr's model um, align with the things that Stern and Gerlach and all the other physicists didn't know at the time. Um, they all kind of conspire in such a way that they could, without making any mistakes, think of this as directly supporting Bohr's model, where the true story is a bit more complicated and convoluted. But let me point out the convoluted pieces and how the misunderstandings of the time actually aligned up so perfectly. So here's the thing that's wrong about Bohr's model. So in the Bohr model, the ground state of atom, like a hydrogen, was assumed to have angular momentum corresponding to n equals 1. Bohr thought in the ground state, the electron should have angular momentum, orbital angular momentum of h bar. If you took any chemistry, particularly college level, you know that to be incorrect. The ground state orbital of hydrogen atom is the s orbital, and s orbital has 0 orbital angular momentum. So in the correct hydrogen atom, the lowest energy state actually has n equals 0. And so the silver atoms that Stern and Gerlach were doing experiment with, it didn't have any orbital angular momentum. What it did have were spin angular momentum. And if you look at the spin angular momentum, so so I'm okay. So let's try to be more correct about this. And so this is the kind of incorrect semi-classical idea. More correct picture is that you would have a, ground state atom, whether it's a silver atom or whether it's a hydrogen atom. And in the ground state, the electron is in s orbital, which means the angular momentum is 0, no angular momentum. But the kind of angular momentum that the silver atom does have is the electron spin. And that electron spin, oh, sorry, that S is going to be confusing because the letter we use for spin is S. The kind of angular momentum it could have is a spin angular momentum, either pointed one way. So this would be the projection of the spin. It could be h bar over 2 or plus h bar over 2 pointing one way, or it could point the other way. So the other projection would be minus h bar over 2. And one might think then, oh, so that could have given a way for Stern and Gerlach to notice that the experimental result here doesn't quite match up with the Bohr's prediction, because this is Bohr's prediction. In Bohr's prediction with a hydrogen atom, so thinking of the orbital angular momentum, you might have had the orbital angular momentum of plus h bar, or you might have had the orbital angular momentum of minus h bar. The difference between these two is different from the difference between these two. Up here, the difference in the angular momentum is total of h bar. Down here, the difference in the angular momentum is a total of 2h bar. So the kind of the separation between the two beams, physics is a quantitative science. We're not just satisfied that seeing the qualitative view of, oh, there's a separation. We want to match up the separation to what should be the magnetic dipole moment of the thing, and calculate it out. And you might say they should have noticed that this separation is half as much as what would have been predicted from Bohr's model. And it turns out um, the amount of the separation you get from the spin angular momentum or the magnetic dipole due to spin angular momentum is actually exactly the same from the magnetic dipole from the orbital angular momentum. And this is how they match up. Bohr magneton is the quantity that we use to specifically talk about the magnetic dipole moment that's associated with the orbital angular momentum. So that's the Bohr magneton. There's a charge there. And you can go through the derivation I want. And what's important to note here is that there's a factor of 2 here. It comes when you are going through the derivation. And is there, yeah. So So yeah, so and without going into the actual quantum mechanics that goes into actually driving this fact, let me just point out this fact. When you look at the spin angular momentum of an electron, um, the gyromagnetic ratio, the ratio between the angular momentum and the magnetic dipole moment, for a quantum mechanical spin angular momentum is twice as large as what you would expect it for a classical angular momentum. So so this is a well, G factor. That's the gyromagnetic ratio, I think. And yeah, and this would be the place where they talk about those two gyromagnetic ratio. So when you look at the one for the orbital angular momentum, it's all what you would expect it to be classically. For the quantum mechanical spin gyromagnetic ratio, there's this additional factor of 2 that takes relativistic quantum mechanics to predict. And that's the thing that they didn't know back then. So if Stern-Gerlach had matched up this separation against the predictions of the Bohr model, they would have seen that it matched perfectly. And so they wouldn't have noticed that the prediction of the Bohr model doesn't quite align with their experiment. So historically, this result is what was interpreted as providing one of the first evidences of Bohr's model. And as I say when we in the lecture when we talk about the Bohr model, it's a semi-classical model. So Bohr is right after all. They were right to, I guess they were more right than wrong to think that, but Bohr was not completely right. This is the thing about semi-classical models. There will be places where they fail. And with the Bohr model, the key place where they fail is this incorrect assumption about the orbital angular momentum of the ground state. And this can really only be corrected in the fully wave mechanical model. And while we don't have enough time to do that properly, we'll look at I think in chapter 8, we'll look at the solutions to the hydrogen atom, or rather the electron wave function for the hydrogen atom. And in that fully quantum mechanical model, we can get nearly all the features right. Um, so I'll leave that there. I guess there are a few things that I didn't quite get to. I will just leave it here that the Stern-Gerlach apparatus is a way that way in especially upper division and graduate level physics, way we introduce some of the truly confusing ideas about quantum mechanics. And there's one such thing covered in one of the simulations. And I think I'll be able to bring this back in a couple of weeks and actually go through some of this. But for now, I'll just point out where that is and so that you can find it. You have to first turn off the HTML5 thing so that you can find this flash simulation. And you have to go through the workaround that I think I described some time ago so that you can run it. And when you run it, going through that imagined workaround, what you will find is this simulation. And what this will help illustrate is some of the truly paradoxical ideas about quantum mechanics. I think I can illustrate this here, maybe briefly without too much explanation. So these are schematized illustration of Stern-Gerlach apparatus. So we are not really we are not really um, um, doing the whole description of the magnetic field and all that. I'm just schematizing it as a way to select one particular spin versus the other. So the first magnet selects for spin up, and when we send the particles through here, we'll find that half of them are spin sideways. And then when it goes through the third filter, this is where classically you might think nothing gets through. Because in the first filter, we selected for spin up. In the second filter, we selected for spin sideways. And when you come to third filter, you might think, oh, I already filtered out all the spin down ones. So there should be nothing going through spin down. But when you actually fire, this is what you end up seeing. Oh, yeah, they go through every once in a while. Um, so sometimes it's blocked, but every once in a while they actually go through. And the numbers you will see once let me make it faster. What you will see is that eventually about 50% of the atoms that go through actually come out with a spin down. But didn't I select, filter all those out? What happened? Where did they get reintroduced? So where we are in the course is not the right place to discuss in detail. But Stern-Gerlach paradox is one that helps the people because the ideas of quantum mechanical angular momentum spin is, I think, one that does an excellent job of aligning your intuition to one that's correctly aligned with quantum mechanics. And I'll find an opportunity to bring this in because it's, again, a little bit outside of our curriculum proper. So I'll bring that back. But for what we went over today is the historical introduction of Stern-Gerlach experiment, which was interpreted as giving support to the Bohr model. But once we understand the quantum mechanics better, it turns out it mistakenly appears to support the Bohr model. But this is one where we say, hey, science is an iterative process. Bohr model is more correct than our previous understanding of atomic structure, and Stern-Gerlach apparatus gives more than less support. So it's more on the supporting side of the Bohr model than the other possible interpretation. I wanted to look at some of the other simulations and just talk about that. I think the biggest one that's really been a long time coming is a Fourier analysis. I think I should finally get to that so that I'm not just talking about Fourier analysis forever without ever doing it. So I'm gonna just run this on, download it and run this on my computer so that hopefully it uses less CPU power than it would if it's running in a browser simulation. So what this simulation does is it kind of makes it simpler some of the calculations that you might have to do. So there might be some point to describing some of the theory in Fourier analysis. So let me write out the expressions that underlies the demonstration you are going to see with the simulation. So I think the good starting place is to imagine kind of a waveform. So imagine a wave as a function of time. Here, the y-axis doesn't matter. It's whatever the wave is. If it's like a signal on your oscilloscope, it might be voltage, and we can make it a little bit easy for ourselves and say that this is a repeating wave. So I'm just gonna think of so I'm gonna only draw and represent one period. So this is one period of the wave or 1.5 period. And what the wave might look like is, so the kind of easiest, the simplest would be, you could have a sinusoidal wave. In the case representing this wave is easy, my function as a function of time is just some amplitude times the sine of omega t, or in terms of this parameter here, it's just going to be 2 pi times t over the period t. That's simple enough. And you can imagine doing similar descriptions even for any arbitrary waves. Imagine you have something like a triangular wave. And if you're trying to write down analytical expression for this triangular wave, let me use letter G. It's potentially not quite so nice. I mean, you can definitely write it out. You can write it out using a piecewise function. You can say, all right, my function is gonna be, let me just let the slope be 1. So my function is gonna be t from 0 to my t equals t over 4. And then it's gonna be this downward slope. So minus t plus plus, I guess, t over 4, so that this point matches up from t equals t over 4 to this point here, which will be 3t over 4. And then it's going to be, again, t from, this time I have to make sure it's starting from minus 1. So, or let me just plug in 3t over 4 here, then it's going to be minus t over 2, I think. Did I do this right? I might have made some mistake. 3t over 4. So this is what I mean, headache inducing. So, but you can work through it. With enough time, you can kind of check your expressions carefully to make sure that they match up here, and if you have an arbitrary function like this triangular wave, you can imagine describing it in the way I did it here. Now, the Fourier decomposition is the idea that even complicated function like this, it can be approximated by an infinite series of functions of this form. So there are coefficients for this sinusoidal term such that I can represent this ugly looking function in this form. It can be represented by an infinite sum, and it goes from, I guess it goes from 1 to infinity. Of sine, you would need both sine and cosine to cover all the bases. I think in this case, the sine alone actually does the job. But if you have other kinds of functions, sometimes you might need the cosines. So my coefficients would be an times sine of, and then this 2 pi t over t, that part remains the same. What changes is now, so this is my fundamental frequency. And for n equals 1. For n equals values higher than 1, that would be my higher harmonics. So n times 2 pi t over t plus, so this is my function that's odd over the period. There's also a function that's even over the period, cosine. So b sub n times cosine of n 2 pi t over t. So that the idea that any kind of complicated arbitrary function that's periodic can be represented by this series expansion in terms of sine and cosine functions, that's Fourier analysis. And that's what this simulation lets you explore, some of these the Fourier expansions. I think it's gonna be a lot easier if we start out with some of the presets. So let me start out with a preset. I think it is a preset for triangle wave. So this is a preset for triangle wave. And I don't know if you can see the colors well here. So you can kind of see it here. Let's see. So so you can see with this red graph, which is just one single sinusoidal function, that you can, as you can see in this sketch as well, it already kind of matches the triangular wave okay. And what these higher harmonics are doing is they are adding a little bit of definition. They are making where this is maximum sharper and sharper with each additional harmonics. So you might see some pattern here. Somehow all the even harmonics are zero. I guess they just work out that way. And these older harmonics, they kind of start out with a relatively small value and they get smaller and smaller. And you can see how as these harmonic values get lower and lower, this becomes less and less a good fit for a triangular wave until where there is no harmonic at all, or yeah, and it's a sinusoidal wave. So I think a triangular wave is one where it's easiest to see how to go from sinusoidal wave to that arbitrary function. It's easiest to see that. And it's also, because it's easiest to see that, it's also harder to see how much broadly applicable it is. So let me show you with a different preset function here. Yeah, square wave is a good one, because that's, you can actually see it here, even with the presets, that with the triangular wave, because this fundamental was already fitting the triangular shape so well, that these higher harmonics, they didn't have, the corrections didn't have to be that big. And so, you know, with a square wave, this fundamental sinusoidal wave, it's a terrible fit for this what out to be a square wave. That's why these higher harmonics are more substantial. It needs greater correction to flatten out this maximum and to add a definition to this transition. And how steep this slope can be is eventually really limited by the highest number of harmonic you get to. You can see that as I reduce the value of harmonics, this steep thing, it gets smaller and smaller. And this is something you can, if you want, you know, if you have like an hour to spend doing calculus, you can work this yourself. Here's one way to do it. There's a kind of a theorem, Fourier's theorem, where if you want to derive these Fourier components, what you imagine doing is you imagine multiplying left and the right-hand side by one of these Fourier components, let's say sine of 2 pi t over t, and then integrating over a whole period. What you will see on the right-hand side magically is that all the terms other than the exact sinusoidal function that you multiplied with will go to zero. You can kind of derive that, or I think I actually do one of the integrals I do in lecture kind of looks like that. So on the right-hand side, the only thing that remains is the coefficient that matches the sinusoidal term that you picked out. On the left-hand side is where you do the calculation, and the calculation you do on the left-hand side will tell you what the coefficient should be. And that's what this simulation is doing, so that we don't have to do those integrals ourselves. And so, you know, if you're into electrical engineering and signal processing, well, this could be very interesting. There are many filters that are built based on doing the Fourier transformation and then doing processing on the Fourier transform and then transforming back. It's a lot of fun. Now, one could easily look at and say, what's that got to do with the quantum mechanics? And I think the tab where it's easiest to show that is under discrete to continuous. This is one where we can show what that's got to do with the quantum mechanics. Let me see here. Yeah, so I think this is where we are looking at the width of wave packet. So let me start out with a place where you might recognize it better. Let's see. I think, yeah, okay. So I hope this is something that you recognize. What I'm showing here is just sinusoidal wave. And why does it have this? things. Okay. So let's just to make sure that we understand all the graphs. So these two bottom graphs, they are both graphed on a similar scale. The x-axis here, they represent, well, x value. They represent the position. This top graph here, it's graphed differently. It's graphing not the x position, but it's graphing these coefficients. If you go back to here and think about these coefficients, what this top graph is graphing are the values of this AN coefficients. So when you have a pure sinusoidal wave, then you have just a single coefficient here. And what it's also showing is that with that pure sinusoidal wave, it has infinite extent. It has to. There's no other way to do it. So in quantum mechanics, we talk about how a particle is better represented with a wave packet, a localized wave. So you think about how you can form a wave like that. And one way to actually do it is to take a wave that looks like this and just to multiply it with something that looks like, I don't know, Gaussian function or something that would localize this wave within that. Then once you have done that, then what you have is not a, so, you know, if you imagine doing this, if you imagine taking that, taking this and multiplying it with a Gaussian function, e to the minus x squared over 2 sigma squared. That's a form of Gaussian. Sigma, it gives you the standard distribution, so standard deviation. It gives you the width of the distribution. Now, once you have done this, then you don't have just a pure sinusoidal wave. You have something that's more comparable to what I had on this left-hand side. Now, once you have that, then you can actually go through the calculation that I was describing just now. You can imagine taking the left-hand side, multiplying it by one of these terms, and then integrating over a period to get the coefficients, AN and BN. And in the simulation, that's what they have done. They gave you a knob where you can change the width of your wave packet. So this sigma x knob is the one that will allow you to localize your particle with to a smaller range of position values. So, okay, let me drag this knob and do that. And, oh, so somewhere here. So as I do that, you see that these two knobs are actually connected with each other. So you might have noticed that when I moved this knob earlier, when I try to make sure that I have only a single component of sinusoidal wave, that this sigma x went all the way to the other side. And as I try to localize the particle, as I try to make the position within a limited space, this knob actually starts moving back. So, so what it's showing here is that in order to represent this modulating waveform like this, you need a multiple components. In fact, if you kind of study AM radio, this is the main carrier band, and these are the side bands, and this is what people use to actually transmit information through radio signals. And so as I try to localize this wave packet, you see that I have to introduce more and more of the other components that was not my initial frequency. And as I localize it more and more, so here's a bit more sideband that's beginning to show. So there's more, and as I localize it more and more. So in order to represent a wave packet that is highly localized within some region like this, it involves many different components of sinusoidal function. And what this graph is, it's showing all those components individually. So at some point it looks super busy. This is showing the sum of all of them so that you can kind of tell what the actual wave will look like. So in the other simulation, you saw the representation of a localized wave, a wave packet. And the wave packet necessarily needs to include the wavelengths, or here it's actually plotting the wave number, 2 pi over lambda wavelength. It necessarily needs to involve multiple wavelengths or wave numbers. So this is where you get a natural connection between the position uncertainty and the wavelength, or through de Broglie relationship, momentum uncertainty. So I think that's probably as far as we'll get into Fourier analysis in this class, which is, mostly at the conceptual level. I won't make you do the Fourier's theorem calculation because it's typically not covered. You can do it. I do highly encourage you to try it out. Try it out with a square wave, I mean triangular wave, but I won't make you do that as a part of any assignment. So yeah, that's what this simulation is illustrating. The connection between the space localization of a wave and spreading out of the wave in the wave number or momentum space. There's a quite natural connection between the two. And note how, other than the invocation of de Broglie relationship, I'm not actually using any quantum mechanical ideas here. All these here, it's just purely mathematical. I haven't introduced any quantum mechanical assumption other than somehow trying to tie this to momentum. That's the only place where you bring in quantum mechanics. Or if you are dealing with just classical waves, everything I said would apply. When you try to make your classical wave localized, that necessarily involves a spreading of the frequency or wavelength of that classical wave. So